Good morning, everyone. What I'm going to go over today is some more shell coding, and we're going to get into actually popping shells today. The last one was with the exit shell code, and it was great for showing you guys how to do it. But now we're actually going to get into the big boy, big girl shell coding. So here's the basic concepts of shell coding. You're going to write your functionality in C. You're going to use strace on compiled the C program that you made, and then we'll haul it apart and find the locate all the syscalls and the arguments that are being used. Of course, we avoid null bytes, which I showed you in the last video, and then we extract the shell code. So enough talking, let's get right into it. So the first things first, when you're writing your shell code, you want to write it in a higher level language first. So, oops. So we'll just write out a basic shell code here. And let's put in system, and we're going to be looking for bin sh for a shell, and close it off and finish it off. And that is that for a basic shell. So what I'll do, I'll save as, and we'll come to our desktop and we'll call it shell.c. And replace, yes. Okay, so now we need to compile that program. So cd to my desktop, and we'll use gcc shell.c, and we'll output it to shell. Okay, so let's run this shell. And as you can see, boom, we have shell. Here we go. Okay, so we know our shell now works. So now, how do we get that down to the machine code, to the shell code level? This is where strace comes in. So now we take strace, and I'm going to use F to find all the forks. With execve, there's of course forking going to happen. It's not going to close the program down behind it. It'll fork new processes, right? New images. Then I'm going to do my expression we are looking for, which is execve, and then I'm just going to run the shell program and see what's behind, because all we know right now is system, right? So like, let's break it down to what's actually happening. And as you can see right here, we have execve with 3 arguments right here. So execve, we're going to have to look that up in our man2 and our uni_std underscore 32.h and find out the syscall and then these 3 arguments here. Then we can start building up our shellcode. So now you understand how writing it in C and then breaking it down gives you different information than you would normally have. So let's close the terminal. We're done here with our C. So now let's go to man2 for execve. And this is the Linux Programmer's Manual. So all you really need here is the synopsis. So we need, in EBX, we need a pointer. EAX, we're going to have the syscall for execve. We'll look that up in a sec. But for arguments, we need a pointer to our bin sh string. So our bin sh, we can't put it in the data or the VSS section. It has to be on the stack to make it executable. So we will use the stack pointer to point to the EBX. We will use ECX and EDX are going to be null. These 2 variables here, the argument vector and environmental vectors, they can both be null for this. So that's all we really need from the Linux manual here. Now we can locate uni_std underscore 32.h, and this one right here will do. And this is where we get our syscalls from. So we're going to cat this, and then we're going to grep for execve, and you can see the syscall number here is 11. So we already know our arguments now, and we already know what we need to put in EAX for syscall. So that's all we really need now to start writing our shellcode. So let's jump right into it. We'll make our executable text section here. This is our start label, which is like main in C, but we call them start labels. And we will start. Now we start doing our instructions. So right away, we knew EAX needs 11 for the syscall. Syscalls always go into the EAX register. EBX is going to be a pointer to our bin.sh string, which we will push onto the stack first with an null terminator. ECX and EDX are going to be null. I'm going to define those right away here because to avoid null bytes, we XOR our EAX register off the get-go. So this is zeroing out the register. So then what I'll do, I'll move EAX into ECX, and I'm also going to move EAX into EDX. So that's EDX and ECX taken care of with the null with null in both. Both have 0. So now let's get right into the EAX. So if I use the full EAX, it's going to leave me null bytes. So I'm going to use the AL, which is the lower 8-bit register. So I'm going to move 11 into AL, which is the lower AL, because AX, the 16-bit, is broken down to AL and AH. So I'm going to put it on the lower part of the register. And I have a mistake. So easy to make mistakes in here. Move. Okay, so now we have that set up. So next I need to push a null terminator onto my stack. So now we use the push command, and I'm going to push, we can use EDX or ECX here. I'm just going to push ECX, and they're null right now. So that's pushing a null terminator onto the stack. And now we need to push our bin.sh onto the stack. So I'm just going to come over here, hex to ASCII here at rapidtables.com is the one I use. And now we need to push bin.sh. So it needs to go in backwards, of course, a little Indian convention with this stuff. So sh, I got to try not to spell this wrong. I did this earlier. So bin, and then I'm going to put 2 slashes. 2 slashes will still work, but this is only 7 bytes. I need 8 just to make sure everything's laid out nice on the stack. And the extra slash doesn't do anything too crazy. So now we have 2 4-byte strings. So this is the sh and slash right here. So I'm going to push and 0x, of course, to denote hex. I forgot my dollar symbol here at the beginning. And so that's our sh pushed onto the stack. We have our null terminator already pushed onto the stack. So let's come back over here. Grab this. Whoops. Fat fingers. And let's fix this. Okay, so now there's something. Oh, there we go. I knew there was something wasn't lining up. So that's our 2 4-bytes there. Now we have ECX and EDX taken care of. We need to figure out EBX. So what we're going to do, we're going to push the stack pointer into EBX. EBX needs to be a pointer to what we're executing. So this will point towards the top of the stack, which is this stuff here, and it will execute it. So move ESP into EB. And that's that. And now we can do our interrupt for our syscall 80. And that looks lovely. So I'm going to file, excuse me, save as, and I'm going to call this one shellcode.s. Yeah, I want to replace it. So let's go back to our desktop where I have everything sort of tossed around. CD desktop. So we'll assemble it. So shellcode.s, I'm going to output it to shellcode.o, make our object file. Okay, so this is just new line, and sort of what I didn't do is hit enter before I saved. Not a big deal. It's not going to cause any trouble. Okay, so now we need to link it. So shellcode.o and output to shellcode. Wonderful. So now we hit shellcode, and as you can see, now we have shell. Perfect. So now we've taken a C program, wrote our high functionality, the functionality of our shell in C, and this is what we do even with the bigger ones as well, and I'll get more into this over the coming weeks. So now we've broken it down into assembly code. Now we need to get our shell code. So let me exit out of the shell here. Now, object dump -d shellcode. Okay, so here's our shellcode, and as you can see, we have no null bytes. Everything went really good. Basically, we XOR'd everything properly, and we use small registers to not let any null bytes exist on in the text section here. And as you can see, it all needs to be in the text section, because if it was in a BSS, it'd be up here and it's not executable. So that's why we had to push it onto the stack instead of putting it in the data section, okay? So now we can do the X copy this one, but that's pretty fucking weak. So let's close this down, come over to my tooling here, and shellcode extraction here. We'll just grab this little command line foo, and now here where it says binary, I'm just going to compile shellcode, and boom, there's my extracted shellcode. Can't get much easier than that. So now we already know this program works good, but let's take a look at running it in our shellcode runner. And I posted this one a while back. If just right in my on my Twitter if you need it. So I'm going to put my shellcode in here. Wonderful, and save. And now I'm going to cd to tooling. Whoops. Now I'm going to gcc f no stack protector, which gets rid of stack cookies, and then zec stack, which disables DEP, so we can execute on the stack here, and then shellcode .c and output to shellcode. Let's try this again. No such file or directory. Okay, so let me just execute code runner. And as you can see, we have our shell and the length is 23. So that's how you work through how to shell code. I hope this was interesting. If you like it, please share with your friends, and I'll be putting out some more, definitely encoding these and setting up a reverse TCP. We do the exact same process. We write it all in C and we break it down like that. So I hope this was educational, and I will be back to you later next week with some more videos.